The second half of 3.6, the related rates portion of this. Rates refers to derivatives. So related rates refers to related derivatives. What the section gets us to understand is that if you have two variables that are related, then their derivatives or their rates of change is related. So for example, if you're looking at blowing up a balloon, if this were a regular class, I would bring a balloon and blow it up and ask you questions about what is all changing as I blow up the balloon. Okay, in the absence of visual aids, I have a YouTube video that I found. I don't know who these people are, but here's a quick little video of a kid blowing up a balloon. Okay, this is actually a lot bigger than the balloons I bring to the classroom. But as he fills it up with air, what's changing? That's what we're going to think about. That was a big balloon. So some things that come to mind would be that the radius of the balloon is changing, the volume is changing, surface area, maybe the air pressure, okay, the temperature. Things are changing and they're all related. Now what you might remember from geometry is that to find the volume you need the radius, to find the surface area you need the radius. So we're going to need to know some things from geometry as well as some concepts from business to be able to solve problems with related rates. Before we get to all that, we have some warm-up exercises. So go ahead and print out this worksheet that says page 1, related rates, warm-up exercises. So we're going to first do some translation. If you see the phrase rate of change, it means derivative. So if you see the phrase rate of change of x with respect to t or in terms of t, it means it is the derivative of x in terms of t. In other words, it's dx dt. So that's how you translate this phrase. The rate of change of x with respect to t is dx dt. Next statement is how fast. How fast means derivative. Is a sale of houses, let's call it S, changing at that instant of time. Time, let's call it t. So how fast, meaning the derivative, ds dt equals what? That is the question. The next one, the radius, let's call it r, is decreasing at the rate, that means the derivative, of 4 centimeters per minute. So in terms of time, okay, time. So the radius dr, the derivative of r, okay, derivative of r in terms of t equals 4 centimeters per minute. Now notice that radius is measured in centimeters, time is in minutes, so they match straight across. That's a unit check. Next one is the supply of tapes, let's call it S, is changing at the rate of derivative, rate means derivative, of 10 packs per week. That's your time. So ds, d, you can use t again for week, or w, equals 10. Now I need to go back to the previous question. Because of the word decreasing, that means that the derivative is negative. Whereas over here we don't know when they say it's changing, whether it's increasing or decreasing. We can leave it at 10. The area of the circle, let's call it A, is increasing at the rate of, rate meaning derivative, 9 pi square inches per minute. So the derivative of area, dA, dt, t is time, increasing, so it's positive derivative, 9 pi, and the units, let's examine those again for this one. Area is measured in square inches, time is measured in minutes, so direct check. Couple more. The volume, let's call it V, is increasing at the rate of 3 cubic inches per minute. Volume, rate, that's the derivative volume, dV dt, is 3 inch cubed or cubic inches per minute. Volumes units match, times units match, very good. The price, let's call it lowercase p, decreased, which means negative, at the rate of derivative, so dp, $2 per week, let's call that t, dp dt is negative $2 per week. Okay, price matches the units, times and week. And finally, how fast is the radius changing when the radius is 5 centimeters? How fast, meaning the derivative, how fast is the radius changing? Derivative of r, the radius, so it's dr dt. Okay, it's all in terms of time. What is that when the radius is 5? So if this was related to the balloon problem, if you had a spherical balloon, let's say it was a nice perfect sphere, and this radius, let's say the radius in the beginning was 0, you didn't have the air in the balloon, it gets bigger and bigger and bigger, and at a certain instant the radius is 5. How fast is the radius changing when it is 5? You might think about when you blow a balloon up, in the beginning it grows faster, and then later on as it gets bigger, it doesn't grow as fast because there's tension, there's only so much space in it, and the balloon could pop. So there's a bit of a stretch of the material, so it starts to slow down. Okay, so these are the warm-up exercises. Now we'll actually do complete problems to see how all this works. So back in the notes, I'm going to remind you of some formulas that you may need in your homework. Area of a circle. A is pi r squared. You may need circumference of a circle. That would be C equals 2 pi r. Volume of a sphere. B is 4/3 pi r cubed. R is the radius of the sphere. The surface area of a sphere. Again, the surface area refers to what would you need if you needed to paint outside a ball or wrapping paper. That's S is 4 pi r squared. If there's anything else you run into in the homework, feel free to Google it online or send me an email and I will let you know. Alright, now we're going to do the second worksheet for this section, and it's labeled as page 2. The first question has pancake batter is being poured into a pan to form a circular pancake whose area increases at the rate of 3 centimeters square per second. How fast is the radius increasing when the radius of the pancake is 5 centimeters? So first of all, the shape is a circle. So we're looking at area. Area is pi r squared. So that's something you get out from the formula from prior knowledge. And then here we're going to translate the area increases at the rate of, that means dA, the derivative of area, dA dt, is 3 centimeters square per second. The units match, and we're good. How fast is the radius increasing? If r is a radius, what is dr dt equals question mark when the radius is 5 centimeters. At the instant when it's 5, how fast is the radius changing? So in order to be able to incorporate all this information into our question, we need to take this and do an implicit differentiation. So we're going to differentiate both sides with respect to t. T is your external variable. It's not in the equation. It's outside. Everything depends upon time. So when I take the derivative of the left side, it's d dt with respect to time. The derivative with respect to t on the right side, pi r squared. So here the derivative is just 1, and so you just get 1 a prime, or dA dt. On the right hand side, pi is a constant, okay, so the derivative of r squared is what we look at. The 2 comes down, 2 pi r. Again, the variables don't match, so I need a dr dt. Okay, this is kind of like the previous section where we looked at implicit differentiation, where we had the derivative in terms of x of y cubed, and the variables didn't match. We said that was 3y squared. Then we had to tack along the dy dx. In the same way, we have the derivative in terms of time of r squared, so it's 2r. The variables don't match, so you have dr dt, dr dt. Okay. Now we know dA dt, it's 3. 2 pi r is given to be 5. dr dt is what we need to find, so we'll keep it there. This is 10 pi, so if I divide both sides by 10 pi, I get dr dt. You can leave your answer in this form, or you can put it in your calculator and get an approximation. Make sure to put parentheses. If you type this into your calculator on your TI 83 or 84, type in 3 divided by parentheses 10 pi, or else it will be wrong. Alright, next question is a business type of problem. It says that suppose the quantity X of Super Titan radial tires made available per week in the marketplace by the Titan Tire Company is related to the unit selling price by this equation. So here's where, rather than you knowing A equals pi r squared, you're given the connection between the two quantities. So we'll write that down, where X is measured in units of 1,000, those are the tires being sold, P is in dollars. Now we need to do some translation. How fast is the weekly supply being introduced into the marketplace? How fast supply is X. So we need to find dx dt, that's the question, when X is 6, P is 66, and the price per tire is decreasing at the rate. Rate means derivative, so dp dt, because P is price, it's negative $3 per week. It's negative because it's decreasing. So this is the translation. This is the given info, what we need to find. Here's the connection. We need to differentiate, both sides, differentiate both sides with respect to t. So I do d dt of the left hand side, the derivative of the right side in terms of t. Again, here the variables don't match. The derivative of p is 1, but you tack along dp dt, minus half is a constant, 2 comes down, 2x, and its derivative of x with respect to t, dx dt. Right side is 0. The 2's cancel. You need to find dx dt. You know dp dt, that goes here, so that's negative 3 minus, you know x is 6, dx dt equals 0. Now make sure you understand you can't combine these there. This is multiply, okay, that comes first. So you move the 3 over, negative 6, dx dt equals 3, then divide by negative 6, so dx dt is negative half. So what we needed to find was how fast was the weekly supply being introduced, but this is in terms of thousands, so I'm going to multiply it by 1,000, and you know that it's negative 500. So as the price goes down, okay, the price is decreasing at this rate, they're not making as many tires available because they don't want to sell too many tires at a low price. Now this problem bothers some students because we don't use this piece of information. But that's what happens sometimes in the real world. You can't use everything there, you have to use what is pertinent. And in this case 66 did not play a role because the derivative of p was just 1, and we add 1 dp dt, whereas x was used because you had an x squared. When you took the derivative, there was still an x left behind. Now there's a homework question just like this. Make sure you check the worksheet when you're doing it. And this brings us to the last question for this section and this chapter. 2 ships leave the same port at noon. So let's say the port is here. They leave at noon. Ship A sails north. Okay, so there's A, at 15 miles per hour. Ship B sails east. East is this way. At 12 miles per hour. It's going a little slower. How fast is the distance between them changing at 1 p.m.? So this is the distance between them. Let's call this side A. Let's call this side B, and let's call that side C. What you'll notice is that in the beginning they both start out at port and the distance between them is 0. But let's say after an hour the first ship is here and the second is here. This is the distance between them. So as each of them keeps moving, the distance between them is changing. and we need to know how fast it's changing at a certain time if they start out at noon. So 1 hour has gone by. 1 hour has elapsed. So what do you think is the distance traveled by ship A? You know, I'm going to rename this as A because that's ship A. The distance traveled by ship B, we'll call it B. So if ship A travels at 15 miles for 1 hour, then the distance traveled A would be just 15 in 1 hour. Okay, so that's that length. Ship B would be 12. We also know how fast each ship is moving. So how fast is A moving? That's dA dt, the derivative, or A prime. That's 15. The derivative of B, how fast this is changing, that's the speed of ship B. B prime is 12. So we have translated the question. What we don't have is a formula. For the first question we had pi r squared. For the second question this was given. For this question, what formula do we know that connects in the right triangle the legs and the hypotenuse? If you're thinking Pythagoras, you would be right. So it's c squared equals a squared plus b squared. Take the derivative of both sides with respect to t, differentiate both sides with respect to t. So the ddt of the left side equals derivative in terms of t of the right side. So you get 2c, the letters don't match, c prime or dc dt equals, this is a sum rule, 2a a prime plus 2b b prime. The 2's can all get cancelled out, just divide everything by 2. We know A, we know A prime, we know B, we know B prime. We need to find the distance, how fast the distance is changing. So C prime is the question mark. This is what we need to find. But do we know C? I'm going to draw a fresh triangle here. At 1 o'clock, and this is 15 and this is 12, we can find this distance by using the Pythagorean theorem. It's 15 squared plus 12 squared, which is 225 plus 144, which is 369. So it's the square root of 369. Okay, so we know everything. Let's plug it all in. So we have C times C prime equals A times A prime plus B times B prime. We know C is the square root of 369 times C prime equals A times, A is 15, A prime is also 15 in this case, B is 12, B prime is 12. So clean this up. C prime would be, that's 225 plus 144, which is 369. We're dividing it by square root of 369, and this is your answer. You can put it into your calculator and see what you get. So what would that be? It would just be the square root of 369, which is, I don't think, a whole number. What is it approximately equal to? Let me use an app on my iPad. Quickly figure that out. Whoops. Square root of 369. Whoops. That's not right. Let's trash that. 369. About 19.21 miles per hour. Alright, so there's 3 different varieties in this section, and you might see 3 or more in the homework. Check the textbook, ask me questions, and get this done.